Hi everyone, welcome to AI Crack channel. This is Akash Hangwar and today we'll be studying differentiability lecture 3. So we are actually meeting after a long time and we'll be continuing the second phase of Rep Master from here onwards. This is QOD19 and again we'll be starting this series once again. Let's take the screenshot for the same. So today we'll be studying functional equations. So what are functional equations? So basically just like equations we have in X and Y, similarly we have functional equations in Fx and Fy. Now the first example says f of x plus y. If f of x plus y equals to fx plus fy, then fx equals to kx. We kind of get an intuitive feeling that, okay, this is true because, uh, if it's a linear function, then this becomes true. Similarly, for exponential functions, we know that this property is true. F of x plus y equals to fx dot fy. Let's say we have a raised to power 2 plus 3. That would be a raised to power 2 dot a raised to power 3. We know that, right? Based on the intuitive feeling. Similarly, for this third example, we know that f of x plus y equals to fx plus fy. Then this is an example of log function. We know that. Similarly, over here, we also know that. But there will be cases where you cannot have an intuitive feeling for the kind of functions we are going to have after solving the functional equations. So for that, we should have one method, right? So let's try to find out that method. Let's take the example one. We have f of x plus y equals to fx plus fy. This we have been given. Now the inherent assumption or the given situation over here is that all these functions are differentiable. So with the help of first principle of differentiability, what we'll get f dash x plus equals to limit h approaches 0 f of x, sorry, x plus h minus fx divided by h. This is the first differentiability principle. Now what I'll try to do, I'll try to modify this expression based on this given equation. Now what I'll do, I'll put y as h over here. So what I'll get, f of x plus h equals to f of x plus f of h. I'll plug this in over here. So I'll get limit h approaches 0 f of x plus f of h minus fx divided by h. So this gets cancelled out. So what will be remaining? F of h divided by h. Now what I'll do, I'll try to modify this again. That would become limit h approaches 0 f of 0 plus h minus 0 divided by h. Now why I'm doing that? Because I have a feeling that if this 0 becomes f of 0, then we'll get a constant number over here. That would become f dash 0, right? So that would become a constant number. And after that, we can find this derivative. So let's try to find out the value of f0. For that, what I'll have to do, I'll put x and y both equals to 0. So f0 equals to f of 0 plus f of 0. So this clearly gives me f of 0 as 0. So our motive is clear from here that f0 equals to 0. Now we'll get f dash x plus limit h approaches 0 f of 0 plus h minus f0 divided by h. This is nothing but f dash 0. Now this is a constant number that is equals to, let's say, k. Now we know that the function is differentiable. Even if we try to find out f dash x minus, we'll get the same value over here. So let's just directly write this as f dash x equals to k. This we have got over here. Now let's try to integrate it. For that, we'll get fx equals to integral k dx, right? That would be kx plus c. Now we know that f0 equals to 0. f0 equals to 0 equals to k times 0 plus c. That would give me c as 0. So basically, fx equals to kx. So this was the derivation for this first example, right? You can similarly derive all these three, but just to clarify, how to derive these equations with the help of first principle of derivability, we did this. Now let's see one example which is a little different from the equations which we have seen earlier, right? So here we have been given f of x divided by y equals to fx minus fy. Now again, we'll start with the same first principle. That would be f dash x plus equals to limit h approaches 0, f of x minus, sorry, f of x plus h minus f of x divided by h. Now I'll have to utilize this over here. Then how do we utilize this over here? For that, I can see we have a subtraction over here. In the earlier case, we saw that we have the summation, but over here we have subtraction. So I'll utilize this and do the reverse calculation. So over here, I'll replace x with x plus h and y with x, right? So x becomes x plus h, y becomes x. So we'll get f of over here x plus h divided by x. That would be equals to f of x plus h minus f of x. So we have done the reverse calculation. Now let's try to plug it in. So we'll get f dash x plus equals to limit h approaches 0, f of 1 plus h by x, x and x cancel out, divided by h. Now again, I can assume that this is 0 over here, and I'll try to see if this value matches with f of 1. So what is f of 1? For that, I'll have to put x and y both as 1. So f of 1 would be f of 1 minus f of 1, right, from here. So that would give me 0. So my hypothesis is correct that f1 is 0. So what I'll write over here, limit h approaches 0, f of 1 plus h by x minus f of 1 divided by h. But over here we have h by x, but over here we have just x. So what I'll do, I'll just multiply and divide by x. So that would give me limit h approaches 0, 1 by x, f of times 1 plus h by x minus f of 1 divided by h by x. So this becomes f dash 1. So we have got f dash x plus, or just x, because the functions are differentiable. It's all already given over here. Fx is differentiable function. So f dash x plus is same as f dash x. That would give me 1 by x into f dash 1. Now f dash 1 is given as 1. So that becomes just 1 by x. Now again we'll integrate it. That would give me fx equals to integral 1 by x dx. That is nothing but ln x plus c. Now over here, if we put 1 over here, f of 1, we know that f1 is 0. We saw that f1 over here is 0. So I'll just do it over. I'll just plug this value over here. So f of 1 equals to 0 equals to ln 1, that is again 0 plus c. That gives me c equals to 0. So this gives me fx equals to ln x. So this is our answer. We have to find the value of f of 1. Probably we have been asked fx over here, fx, not f of 1. F of 1 is clearly 0. So let's talk about graph-based questions and see what kind of questions can be framed under this category. Let's say we have been given this graph like this, and we have been asked to, find out the points at which the function is non-differentiable. So for graph-based questions, we'll have to see at the function, the points where the function is not continuous, that is this point, and because the point is actually missing over here, the value is not defined over here, and sharp edges, sharp corners basically. So 1 point over here. So these are the 2 points where the function is non-differentiable. Or we'll have to see the edge points as well, because once we have been given a particular range or the close range, we have to see the differentiability at endpoints as well. So but eventually we can see that over in this particular graph, only this point and this point are the points where the function is non-differentiable. So this was just an example. Let's see how it actually looks like. So let's see this example. The function fx equals to maximum of 1 minus x, 1 plus x, and 2. Here x belongs to, this should be minus infinity to infinity. It's incorrect over here. And we have to plot the graph, and we have to see, we have to check all these options, right? So let's try to solve it. So the first function is 1 minus x. So we know that if fx equals to minus x would look like this, will pass from 0. So basically adding 1 to it would make it like this. This would be our 1 minus x. This is y equals to 1 minus x. Now similarly for 1 plus x, x passes, y equals to x passes through origin, looks like this. So 1 plus x would be looking something like this, both passing through this point, right? Because if we plug in x equals to 0 over here, we'll get 1 over here in both the cases. So that's why. So this would be x equals to 1. This would be minus 1. This would be, sorry, this is not x equals to 1. This is y equals to 1. And this would be 1. Now we have to plot y equals to 2. So for that, that would be a straight line. That would be y equals to 2, this point. Now we have to find the maximum of these functions. So we can clearly see that from minus infinity to minus 1, this particular function y equals to 1 minus x, that is the maximum. From minus 1 to 1, this constant function is the maximum function. And similarly, from 1 to infinity, y equals to 1 plus x, that would be the maximum function, right? Now, so we got a function of, this sort. This point is y equals to 2. This is x equals to minus 1. This is x equals to 1. So this is the function we got. Now this is continuous at all points. Yes, it's continuous at all points. Is this differentiable at all points? No, it's not. So this one is correct. This is not correct. Differentiable at all points except x equals to 1 and x equals to minus 1. Yes, that is correct. It's not differentiable over here because we have a sharp edge over here. This sharp edge, right? So yes, this also correct. Continuous at all points except x equals to 1 and x equals to minus 1, where it is discontinuous. It's not correct. It's non-differentiable over here, but it's continuous over here. So this is how we have to solve this question. A very standard question, and these kind of questions can come in PGDBA. Now let's try to solve another example. We have been given one function fx equals to 1 plus mod sin x. Now let's try to solve it. Fx equals to 1 plus mod of sin x. Now forget about 1 over here. Let's try to plot sin x, mod sin x first. So for that, we'll see this is our sin x graph, right? But we have to take modulus of it. So what we'll do, we'll just invert the negative part. So that would become like this. So in short, what kind of function we'll be getting? We'll be getting something of this sort. And these points are 0, pi, 2 pi, basically n pi. At all n pi points, we'll be getting a sharp corner, right? Now, we just have to add 1 over here. So this is our origin line. What I'll do, I'll just make it over here. So this becomes our 0 point, right? So basically we just added 1 over here. So this becomes 1 instead of 0. So everything is added with 1. So that's how the function looks like. Now, first option says the function is continuous nowhere. It's actually continuous everywhere. Even if you extend it till minus infinity or till infinity, the function is going to be continuous. It's not going to be discontinuous anywhere. So this is wrong. Continuous everywhere, this is correct. Differentiable nowhere. That's not true because we know that it's differentiable at all these points. It's just indifferentiable or non-differentiable at only n pi points, right? So this is not true. Non-differentiable at x equals to 0. That's correct. At x equals to 0, it's non-differentiable. That is true. Non-differentiable at infinite number of points. That is also true because from minus infinity to infinity, you will get many points, many multiples, infinite multiples of pi basically. So at all those multiple of pi, you will get infinite points and basically infinite number of points where the function is non-differentiable. So this is also true. So this is how you have to solve these questions. These are very simple questions. You just have to plot the graph correctly and They have the basic understanding where the functions are differentiable and non-differentiable, and discontinuous and continuous, and you'll be able to solve these questions. So today's lecture was still here only, and with this we have almost covered the entire syllabus of differentiability, and we'll start with the methods of differentiation from the next chapter. So let's catch up tomorrow with another lecture of methods of differentiation, and thanks for watching.